Today we'll be dealing with one of the most complex concepts in molecular dynamics simulation, which is called umbrella sampling. This is a very powerful technique used in protein ligand simulation, especially to understand the binding interactions and to calculate the potential of mean force, which is called PMF, that gives insights into the free energy landscape of the binding process. And it helps to understand the binding affinity, the energy barriers, the sampling difficult to reach different states, overcoming energy barriers, comprehensive sampling, and accurate free energy calculations. In my previous video, I have shown you how to perform MMPBSA or MMGBSA to calculate the free energy calculations. But this umbrella sampling technique is even more accurate to calculate the free energy calculations based on potential mean force, which is the force. So it helps us to understand the bound state and the unbound state. So this is the bound state over here, and when it moves away from the receptor, it becomes unbound. So we need to understand how much energy is required to be in the form of bound state and to be in the form of unbound state. So we require the energy. And what are the forces that act upon this? And we sample them, individually at different intervals, and then we identify this technique to understand the free energy calculations, which is a very powerful technique and very complex technique as well. So it requires supercomputer, high performance computing center, or your laptop has to be much more efficient to calculate different samples at different intervals and to perform free energy calculations. So how it helps? It helps. The practical applications are in drug designing and protein engineering. So in pharmaceutical industry, umbrella sampling is used to predict how well a drug molecule will bind to its target protein, which is a critical factor in drug efficacy. And in protein engineering, it helps to understand how mutations in a protein might affect its binding affinity for different ligands, guiding the design of proteins with the desired binding properties. So it gives you a detailed mechanistic insights, and by analyzing the potential mean force along different reaction coordinates, you can gain a detailed understanding of the mechanism of binding, including the role of water molecules, the ion interactions, or any conformational flexibility of the protein. To understand umbrella sampling, let's take an example of a dog walking up the hill. Okay, so let's imagine that you are with your dog and you want to climb a hill with your dog. Okay, the point of the hill represents the landscape of the system. The bottom is the low energy, which is the stable energy that you are standing right now at the bottom of the hill, and the top is the high energy state. And the dog represents the molecule in the system. So starting from the bottom up to the top of the hill is presented as a reaction coordinate. And what is the problem? The dog might get stuck halfway due to lack of energy, like a molecule in local energy minimum. Okay, so how it works is the hill represents the energy landscape of the system. The bottom of the hill is, let me show you with this, the bottom of the hill. This is the bottom of the hill, which is the stable state. And this is the high peak of the mountain, which is the highest state of the energy. Okay, so you need to travel from here to here. So the dog is a drug molecule, and its position from here to here is the reaction coordinate. Normally, the dog might not be able to climb up the hill all the way on its own, so you have to drag him somehow. So you will be standing here and you will be dragging him. You stop at different points along the way to let the dog rest and explore, then pull it a bit further. So this is like applying a series of gentle forces to guide the molecule along the reaction coordinate. So this is the small energy that you are exerting on your dog, and it helps to climb all the way up to the hill. At each stopping point or window, you are making sure the dog or which is the molecule in the dynamic simulation or protein ligand complex, stays within a certain range of positions. So over time, you gather information about how much effort, energy it takes to keep the dog at each point of the hill. So you collect this energy, this energy, this energy, which is called conformational sampling. So generally, if you have performed DFT calculations, so if you are into quantum physics, you might have seen this particular example where you can see that how a molecule tries to interact with you call it as a receptor, and this is the molecule. So how much energy is exerted on that molecule to stay in the global minimum rather than in different local minimum. So if you perform this nudge elastic band calculation, so which is called NEB calculations in quantum physics, so this is exactly similar to what you achieve in umbrella sampling also. So this is the landscape itself. Okay, so we are calculating this potential mean force along all the conformational samples and to identify how much energy is required to be in the stable position up to the highest position. So in summary, the dog example is like helping your dog climb a hill using a leash. So by guiding the dog up the hill and observing how much effort it takes to keep it at different spots, so you can figure out the energy needed to move from the bottom to the top. And this technique helps scientists to understand the energy landscape of molecular processes that might be difficult to study directly. As I said, you gather all the information at different intervals where you stop and observe the efforts needed to keep the molecule or the dog in that particular position. And finally, you combine all the information from all the points to understand the overall energy landscape. So I would like to thank the author Yakin, who has developed this particular tool called CHAPERONg, which is much more efficient to perform umbrella sampling. So if you follow Gromacs tutorial by Justin Lemkul, it might be overwhelming to you at first, because when you see that tutorial, you might be thinking that is for amyloid beta 1 to 42. Tutorial is not for protein ligand simulation. So in my last video, I have shown you how to do the post-processing analysis of protein ligand simulation. So in continuation to that, I'll be dealing with the same, not the same example, but in terms of protein ligand simulation, how to perform umbrella sampling for protein ligand simulations. Okay, so we'll be dealing with this particular tool called CHAPERONg, which makes much more easier to perform umbrella sampling. You don't have to, perform each and every step individually, but you can perform it in a very nice way, which will help you to even further perform many simulations of your complex systems. In conclusion, umbrella sampling helps in protein ligand simulation by providing a detailed quantitative picture of the binding process, and it ensures thorough sampling of the binding pathway, allows the calculation of free energy profiles, and helps in overcoming challenges related to energy barriers and sampling efficiency. And this makes it an essential tool for understanding and optimizing molecular interactions in bioinformatics and drug designing aspects. So we'll be dealing with CHAPERONg today, and let's get started. You might have seen this page, which was provided by Justin, and these are one of the famous tutorials in Gromacs. So we'll be dealing with umbrella sampling, but not this one. Rather, we'll be using the CHAPERONg, which I explained before. Okay, but before understanding the theoretical and practical concepts of umbrella sampling, you should be able to perform lysozyme in water, this particular simulation, which I also made a tutorial on. And also you need to understand the protein ligand complex as well. And if you want some more details about the theoretical and practical aspects of umbrella sampling, then you should read this particular article by Justin. and it provides a detailed understanding of umbrella sampling, how it has been done. If you navigate to this particular website, they will tell you how to access this repository. So you have to click on this particular GitHub repository, which I clicked already, and then you have to download the whole repository. So once you download that, what you have to do is you have to place this particular folder somewhere in your home folder. Okay, if you are using Mac, then it might be your home folder like this, but if you are using Windows, then you can place it in the C drive. Okay, so once you place that, what you have to do is, I have already installed so that I don't have to, but I will show you. The first command that you need to provide is you have to give the permission for the file. So the file that you are going to install is this one, install chaperong g.sh. Okay, so for that you have to provide chmod plus x install chaperong g.sh. Okay, so you have given the permission. Now you can just type / install chaperong g.sh and then you click enter. I have already installed it, so I don't have to, but once your setup is complete, so I press no. Once your setup is complete, you will see this particular screen. I mean this dialog box. This dialog box will tell you that your Chaperong G has been installed. Okay, so how to verify that? So in your case, in Linux, it should be the shell that you are using is bash rc. So you can check your bash rc cat dot bash rc, and you will see that your Chaperong G has been installed over here. To uninstall that, you just have to remove this command from here, and that's it. You are done with the uninstallation. Okay, so now you can see that your Chaperong G has been installed. Now what you have to do is, the command to run Chaperong G is run chaperong g.sh, and -h is for the help. So this is how you can install the Chaperong G, and I will tell you in the next section how you can perform umbrella sampling for that. But before that, there are some requirements or dependencies that you need to install alongside this particular software. So if you navigate here, you will see that they have mentioned that you have to install all the other dependencies with Conda environment. If you look into the directory, they have provided a YAML file with all the dependencies over here. You look into the other file, which is conda environment.setup, you will see that they have provided the configuration to set up the conda environment. So what you have to do is you have to run this in order to install all the dependencies that you have. To do that, what you have to do is you just have to give the permission, which is chmod plus x and the conda environment setup.sh, and then / conda environment setup.sh. I have already installed so that I don't have to, but it will take some time and it will be installed within a couple of minutes. So once this is set up, and you can see from here my conda environment has already been set up over here. After that, so once the conda environment is set up, you have to activate that environment. So that you can do by using this command called conda activate chaperong G. Remember, in the YAML file, there is no Gromacs installed. There is no Gromacs installed. So what you have to do is, and this is the first step that they have mentioned, that you need to install Gromacs first, and then you can perform. In that same environment, you can do conda install Gromacs. I have already installed, so just to verify that, you need to type gmx, and if it works, that means your Gromacs has been installed. So you just have to keep in mind that you have to install Gromacs once the conda environment is set up, and that's it. You are ready for umbrella sampling. Now let's do umbrella sampling. They have provided a very nice tutorial on umbrella sampling, so you can exactly do the similar setup for your simulation as well. The first thing that you have to do is you have to understand what the other tutorials that they provide. I mean, they have performed the same analysis for protein in water. I mean, this Kelch domain in water, then this Kelch domain with the inhibitor complex for protein ligand simulation, and then they also provide this umbrella sampling tutorial. Head over to this particular section and download the files. So to follow along in this tutorial, you can click here to download a folder containing all the input files for the umbrella sampling simulation, and extract the folder and navigate to that directory. So if you download this, now it's downloaded. So you just extract it and go to here, and these are the input files for the system. So what are the input files? We can just navigate to the directory, look into the contents. So ls-la, and you can find the mol2 file for the ligand. The ligand name is IQK, and the str files. This str file has been generated by using CGenFF server, and the whole simulation is based on CHARM force field. Okay, and they have used CHARM 36 July 2022 force field, and they have extracted this particular cluster, or I would say the protein ligand complex, from the previous simulation. So we'll be using this particular PDB file, the complex file, for the umbrella sampling simulation. They also have provided the ions.mdp file, umbrella sampling pool.mdp file, the umbrella.mdp file, and the minimization.mdp file, npt.mdp file, and npt umbrella.mdp file. You know, it's a lot to do. I mean, there are many more calculations that you have to perform, but if you perform individually, it will take more time. But by using CHAPEROng, you can automate this workflow if you have all the files together listed over here. And one more important parameter or file is called parafile.par. This is the parameter file where you set all your settings. Okay, let's open this parameter.file, and you can see this is an input parameter file for CHAPEROng. So lines beginning with semicolon are comments. So lines beginning with the hash are disabled or unset parameters. These are some general parameters where the input file is .pdb or .grow. From the previous simulation, you can extract the grow file, or you can convert into PDB file, and then you can use it as an input file. Mostly all the simulation box type that defaults to cubic. You can also use dodecahedron, triclinic, octahedron. Number of threads to use: if you are using laptop, you can set it to 4. Okay, and if you have a GPU, you set it to GPU, otherwise CPU. And the water model, whether you are using SPC or TIP3P, that you can refer what type of solvent model you are using, or the water model that you are using. And rest of the parameters, for instance, the positive ion is Na and the negative ion is Cl. Okay, and the salt concentration is 0.150. You can set to 150. I mean, that's the default concentration. And for simulation temperature, you can set to 310 or 298. It depends on your previous simulation that you have performed already for the protein ligand calculation. And then the trajectory file has to be center. You can also use the fit. You can provide the GMX path. You don't have to provide the GMX path because we just recently installed Gromacs in your Conda environment. They have provided these parameters specially for the umbrella sampling simulation. And this is the file that will be your input file. These are the ligand file. This is the parameter file for CHARM, and we'll be using this script. So your Conda environment is already set, so you don't have to do anything. You just have to download these files and set your files accordingly if you are doing your own analysis. So let's run this command to perform umbrella sampling. So what you have to do is you just copy this command and then press enter. So it will prompt many different parameters, and it will ask you some inputs. So the first thing that you have to do is what type of simulation do you want to run. So it will be number 2, that is enhanced umbrella sampling simulation, number 2. Okay, and then they will be asking what type of system are we simulating, that is protein and ligand, number 2. And then this will ask you step to begin resume a workflow. So what step that you want to calculate. So we'll start from the scratch. So that's why we prepare the protein topology first. So that will be 0A. And it will ask you what is the ligand name. Remember I mentioned that ligand name is IQK. The name of your ligand you can find in your topol.top file. So in here the ligand name is IQK. Okay, then press enter. So it will start generating the protein topology, and it uses CHARM force field, that is CHARM 36 July 2022.ff, and it's done. So before you proceed, ensure you modify your topology to indicate the immobile reference for your pooling simulation. When you are done, enter yes below to proceed to the unit cell. They have already defined it, so I just type yes and it will proceed. Now it will ask you which platform have you used for your ligand parameterization. So I mentioned that there is a tool called CGenFF. So you can go to this particular website and you can create that .str file by uploading the mol2 file. So if you upload the mol2 file, it will generate a str file, and this str file is nothing but the CHAM parameters for your ligand simulation. So that's what they are asking. So how you have parameterized your ligands. So there are many options. You can use CGenFF or LigPartGen or ProDrug2, that is for Gromacs force field. Since we are using the CHARM force field, we'll be using the CGenFF server. So press 1. Okay, and it will ask you whether you want to convert the stream file .str to Gromacs format. Yes, so press A. So it will take some time, and it will convert your CHARM stream file .str to Gromacs format. And while it is running, you can see here how the files are being converted. Okay, so it will use the script called CGenFF CHARM2 gmx.py3 nx2.py, and it will convert your str file to Gromacs form. Now it's done. The CHARM topology of the Gromacs format is done, and you can see the top file and the grow file, etc. All the files have been generated. Now they are preparing the protein ligand complex. So the protein ligand complex is done. Now modifying the topol.top. So it will automatically add the IQK ligand to your topology file, and you can see here how it is being added to your topology file. Here they have added the IQK topology file. You may want to check the new topol.top now to verify the modifications. I mean, I have already verified it, so you can proceed with yes. And now you have to define the simulation box. This is the default simulation box, but in here they have mentioned at the prompt select 1. So here what you have to select is 1. You have to provide the dimensions number 1, and then you can provide the center dimension XYZ. Okay, and then you have to define the box dimensions. And you can see that the values, why they have modified these values, the values above have been arrived at by adjusting the coordinates such that it is wide enough to contain the complex even after pooling simulation whilst taking the care of the periodic boundary conditions. Okay, so that's why they have modified it. And then now you press 2 and proceed. So defining the box is done. Now solvating the system, and it will be done automatically because you remember you have added the parameters of ions in your parameter file, and it will automatically add the ions. Okay, now the minimization will be done. You see, yeah, it starts minimizing 50,000 steps and it will be done automatically. So you don't have to individually perform all the commands. So that's the beauty of this particular tool. It is doing all the calculations automatically. You just have to type the prompts. So I'm going to stop it and I'm going to show you, because it will take some time, and also you need to have a better CPU power or GPU power to perform all these calculations. So I will show you how I have done this previously and what files have been generated already. So I'll start from the beginning. So you can input this command, and this is your parameter file, this is your input file. Okay, the first command is 2 because we are doing umbrella sampling. The second command is a protein ligand simulation, and then the input parameter is 0a because we have to prepare the protein topology, and then you provide the name of the ligand file. So it generates the protein topology based on CHARM 36. Okay, and the next thing that you have to do is, before you proceed, ensure you modify your topology. So yes, and then you provided the platform CGNFF, that is option number 1, and you need to convert CHARM stream file to Gromacs format, that is option number A, and then it starts converting your CHARM topology to Gromacs format. So it's done now. It has been added to your topology file. And do you want to proceed? Yes. And then defining the simulation box, that you have to define your box dimensions. So once you define that, you need to press 2, that is proceed, and then it will be adding the ions, the solution box with the ions, and now it will start doing the minimization. So here, the minimization, and you can see the minimization has been done over here. And this is your potential energy, maximum force, and normalization of the force. Okay, so once this is done, it will calculate automatically the energy calculations for your post energy minimization thermodynamic parameters. So how you can see that is, if you go to the downloads, I have already done this, so that's why I'm showing. So if you go here, there it will create a folder called post EM thermodynamics, and it will generate the plots automatically. You see, this is the potential energy done. So the next thing it will ask you is that, do you want to define the index file? So what you have to do is here, do you need to make custom index groups before proceeding? You press no, because it will automatically handle the index file by combining the protein and the ligand automatically. So you don't have to type yes here, you have to type no, and it will automatically create index group of protein and your ligand. Now, do you want to run an optional NVT equilibration? You press no, but in some cases, if you want NVT equilibration, you can press yes, and then it will perform NVT equilibration. So in the tutorial, they mentioned that you have to press no. So skipping NVT equilibration and proceeding to NPT equilibration. Okay, now running the NPT equilibration, it will take some time. So it generates the configuration file, and then it will run NPT equilibrations. So here you can see my NPT equilibration is already done. Now calculating the post NPT thermodynamic parameters. So once this is done, it will calculate the energy, that is the NPT pressure. Here the pressure, because this is NPT simulation, and then it will calculate the density. So density and your pressure. So now everything is done, all set. Now it will perform the steered MD simulation. So what is steered MD simulation? You can see. So the n steps, dt, and the pull coordinate rate parameters set in the mdpull.mdp file contained in the folder that you have downloaded indicated that we will be pulling the ligand away from the receptor for 500 picosecond over a distance of 5 nanometer in the z direction. So like this. So they want to pull it 5 nanometer distance away from the bound state to the unbound state, and they want to perform this steered MD simulation. So yeah, you can adjust these parameters based on your specific cases. The output files of the pulling simulation, including the ones shown in the figure below, are saved in the folder called steer.md. So here you can see I have already performed this MD calculation, and it took good amount of time for me because I have been using CPU. So now everything is done, and you can see that steered MD simulation is complete. You can see the folder with all the graphs. So this is the displacement, this is the pull F coordinates and the pull X coordinates. And now they will extract number of frames and simulation duration from the trajectory. So now here, yeah, these are the coordinates that they have generated from the steered MD simulation, and you can see there are 200 GRO files that have been generated from the steered MD simulation. Okay, so number of frames in the trajectory is 200. Now use this pull.xtc file and pull.tpr file to pull the trajectory, and they will start preparing to extract the 200 snapshots. So it will again take some time. So it's all automated, you don't have to do anything, you just have to provide the initial parameters and it will run automatically. Okay, and you can see it starts doing the calculations. So after extracting the frames as images, so it will create a movie here, movie.smd, and you can see this movie. Okay, it will create a movie by using PyMol, and this is the GIF that they have provided. So after that, it will ask, do you want to proceed with the umbrella sampling? Yes, and then it will perform the umbrella sampling. So once this umbrella sampling is done, so here everything is done. Now it will create two files, which is pullf files.dat, pullx files.dat, tpr files.dat, and then your umbrella sampling pullf and pullx. Okay, these files will be used for further plotting parameters. So for that you can use WHAM, where you provide the tpr files.dat and pullf files.dat, and it will create a histogram using the unit kilocalories per mole. So you can read the documentation from the Gromacs website as well, because they have also provided the same thing. They have explained data from here, and now you can see my umbrella sampling results. Okay, I have done it for smaller duration because of lack of high performance computing thing, but you will find a similar graph for your umbrella sampling simulations. So they have also provided that, and you can find the similar graph. So this is how you can do umbrella sampling simulation, and the calculated free energy of binding delta G is written to the file called summary.dz.dat. So yeah, this is a very nice simulation that you can perform for your protein ligand complex to accurately predict the binding free energy. So this is how you can extract the potential mean force curve for your umbrella sampling, and you can perform the WHAM analysis as well, and all the files will be generated over here, so you don't have to worry. Okay, one more thing that I want to mention, that if you go to the posts over here and you go to the series article collection, and you can see all the tutorials provided by them. So you can start with MD simulation, ubiquitin in water, then the Kelch domain in water, and then protein ligand complex, and this is the umbrella sampling. And you can also look into what are the parameters they have for CHAPEROng G. This is a very nice tool, and I would say you can use this tool to perform automated stuff for your simulation, but also remember that you have to carefully check each and every file every time when you perform certain simulation for that. And if you need any documentation or help, you can visit this particular website to understand what are the theoretical and practical concepts associated with it. So yeah, this is how you do umbrella sampling, and if you have any doubts, you can ask me in the comments and I will try to answer them, or you can reach out to Yakin for this, and he will explain you what are the problems that you are facing, and I also can help you to set up the parameters for your protein ligand simulation. If you want me to make some more tutorials like this, then please subscribe to my channel. Make sure to comment, like and share. Thank you very much.